Welcome, this is the midterm demo for Group 15. Our project name is SecureScape.
For a quick intro, SecureScape is just a network of devices used for real-time threat detection in remote areas. Through the course of this midterm presentation, we'll begin with an overview of the project for context for the viewers, then a hardware breakdown of our current parts we're using for the demo, then demos of our overall functionality, and two demos of our engineering specifications with analysis of those results, and then finishing off with some of our challenges and our next steps towards completion of this project. All right, so just to give more context regarding our project, this is the overarching setup, starting out with our gadget in the middle, the ESP32S3. It serves as the central hub for notifications as it's where the micro router is held. This can trigger the peripherals as a node, and it also acts as the medium for communication between the mobile app and the node, which can also trigger more of the peripherals. And then the node is where most of our active outputs are held, with the alarm and the light. And it's also where motion is detected through the PIR, and then images are captured with the ESP32 cam, then sending messages over the HTTP to the gadget, and then that being seen by the mobile app to then trigger the notifications.
The next section will be focusing on the hardware, specifically the parts and subsystems, which will be headed by Dylan Myers and myself, Philip Morona. Our node has many peripherals as shown on the slide. The passive IR sensor will be pointed towards the testing area and will respond to movement by setting a pin high, which will trigger the buzzer alarm and capture an image of the testing area. We have included additional functionality for the user to illuminate the area around the node. For now, we're just using a single LED, but our final demonstration will be a cob LED strip, which circles the top of the node.
For our gadget hardware, we have three toggle switches simulating our control switches that will be integrated into the final device, so allow for alarm activation and lighting control. We also have a micro router that serves as a central network enabling HTTP communication between the node, the gadget, and the mobile app. And the image on the far right displays the gadget setup, including power connection, serial monitoring, and test LEDs that align with the switch operations. For PCBs, the current state, they are not finalized, so they were not used in the demo. They have functionality but need further refinement. But they do have functionality. They can push code and trigger their specific peripherals. The next improvements would be optimizing power distribution, data reliability, and better system integration. And our next steps moving forward are finalizing these enhancements and then begin full-scale testing for real-world validation.
This next section of our demo, we will be going through the overall functionality of our system. We will be demoing person detection and response, mobile app control, and then gadget control. The tests that we will be performing to show overall functionality for our system will consist of three tests. First one will be person detection and response, where the PIR will detect motion. Our person detection algorithm will run on the image captured after motion has been detected, and the alarms and LEDs will be sounded accordingly. After that, a notification should be sent to the mobile app. For the second test, we will be testing mobile app control. We'll trigger peripherals from the phone, and our nodes will receive the command and activate the corresponding peripherals. The third test will be gadget-controlled activation. Gadgets will send a command through activating switches, and then the nodes will respond by triggering the assigned peripheral.
Just as a heads up on the next three slides, we use our alarm to test as it's one of our peripherals on our node. And at certain points, that audio gets really loud, so I recommend turning your volume down just so you don't hurt your ears. All right, so this is the main focus of our project. First off, once motion is detected through our PIR, then the image processing algorithm will be triggered on the captured frame. And then if a person is detected, it will trigger the peripherals and then send a notification to the mobile app, as you can see in the video.
So this is our gadget. This is the breadboard configuration we've got going on. And then these are the switches. These are the hardware peripherals for the gadget. That's like a control hub for our system. So we've got trigger alarm, our buzzers right here. And then so that just triggered the alarm, and then this turns off the alarm and the lights. This is just like a check pin to make sure everything in our system's working correctly, so disregard those. But then we have turn on the lights right here, and the light got turned on, and so that should turn it off. And yeah, that's our gadget functionality.
So this is our buzzer, our lights. This is the node, and we've got all the hardware peripherals set up for that. We're going to be showing functionality for the front end, the other control hub. So we've got trigger alarm, turn on lights, and turn off lights. So he's going to trigger the alarm. That should, start going off, and then turn off the alarm. Alarm turns off, and we're seeing all the commands in the serial monitor because we're monitoring the gadget just to show more functionality in our system. But that should turn on the lights, and then now he's clicking turn off the lights, and we're set.
We will now be entering the third section of our midterm demo, where we will be demoing 3 key engineering specifications for our system. Those 3 specifications are detection accuracy, response time, and detection range.
In the following slides, we will be demonstrating our system's detection accuracy, response time, and detection range. To detect accurately and for fast response times, we need reliable communication across our devices. Detection range is mainly a hardware limitation of the passive IR sensor, but even when movement is detected, our system must reliably react within a minimum of 5 feet away.
Alright, this test is pretty similar to our main functionality, just if motion detected, trigger image processing, then if person detected, then trigger the peripherals, and then trigger the notification. So in this video, you can see that where it's me waving my hand, just making sure movement's going through, and then the notification's received, and then shortly after Jackson comes in, waving his hand, making sure the notification going through, and then Philip, and then as you can see, the notifications are going pretty quickly. There's really not much delay.
The results from our detection accuracy demo were quite impressive. We achieved an 80% detection rate across 10 test runs and observed that detection accuracy decreased as we moved further away from the camera. While person detection remained consistent, delays in data transfer due to HTTP affected mobile notifications, contributing to less than 100% functionality rate. Our results established a strong baseline, and we have identified key areas for improvement, including refining detection range and optimizing data transmission for more reliable and faster notifications.
Go. Go.
I don't write software. That doesn't work that way.
Go.
Which game? UF and UCF? No, I got in too late, and then I did something very stupid.
The response time varies within quite a large margin. We've concluded that the delays are most likely due to network latency within our HTTP communication between the ESP32 CAN board through the router and populating images on the app. Another potential bottleneck would be the lack of memory in our microcontrollers. We understand that response time is paramount in every real-time system, and we're focused on improving this aspect of our project.
We're going to start at 16 feet and move forward, and whenever the blue LED on the device down there triggers, then we know that a person was detected. So we're going to go with that. Okay, there we go. Take that step forward. That's like, let's say 15 feet, honestly. All right, so we're testing from 10 feet here. Just to see, let's make some motion, wave our arms. Here we go. So this is the test one at 5 feet. I don't want to move too much because it's going to trigger, but then we start making motion, and there we go. From our detection range test, we can definitely say that we have a confident baseline. We were able to get a person detected at each of those distances up to 15 feet. But again, as noted, the further away you were, the longer it took for, like me, while moving to get detected. It got up to like 20 seconds while I was at 15 feet. But sometimes it would be faster, sometimes it would be slower. It just depended, but it was definitely slower. But then for the incremental test where the light would just trigger as I moved in slowly, we were getting pretty solid distances around 5 to 7 feet, which is above our engineering minimum specification. But there's definitely some issues with HTTP response time, sending the messages to trigger the lights, which we can definitely then improve upon.
Current issues and what's left, response speed and notification accuracy still has room for improvement. While our system is functional and we still aim to enhance the performance further. And we do have a strong baseline already exceeding the minimum engineering specs. The system is consistently detecting motion and sending notifications, but further refinement will improve real-world robustness. With additional improvements, focusing on enhanced mobile app notifications and improving detection accuracy in varied environments, ensuring reliability of operations across different conditions. And our next steps involve implementing the corrected PCBs, conducting thorough testing, and integrating them into the constructed housing before final verification for the demo.
Thank you for watching our midterm demo.